Okay, guys, so welcome back. We're gonna do this Brayton cycle, but it has some differences from the typical Brayton cycle that we have seen. A typical Brayton cycle is for the production of electricity, okay, to produce mechanical power out of the turbine, okay. Its basic components are a compressor, a combustion chamber, and a turbine, and a gas turbine. In this case, we're gonna look for a Brayton cycle that has more machines because it's intended for another thing. Its purpose, it's propulsion. So the basic idea is to accelerate an incoming flow of air. Okay, these things are mounted below the wings of planes, and it's one way to propulse vehicles through air, for example. Yeah, so these Brayton cycles are meant for propulsion. In that case, we will have certain differences with our typical Brayton cycle for production of electricity. Okay, well, these are the differences from, look at the states first. So I have put here 0 state, 1, 2, 3, 4, and 5. Yep. Now look at the compressor. We still have the compressor. We still have the combustion chamber and the turbine. But now we have two more elements, which is the diffuser at the entrance or before the compressor, and we have the nozzle at the end of the cycle. Okay, the diffuser is meant to pressurize a little bit the incoming air, and the nozzle is meant to accelerate full. I was gonna say full throttle, but I don't want to mislead you. This is not a throttle. Okay, this is not a valve, but as much as we can in the nozzle. Otherwise, we won't produce thrust. And if we don't produce thrust, the plane won't move. Okay, that's the basic idea of this stuff. I'm going to give you already the data. Okay, I'm going to give you the data. First, look at the blue things inside the diagram, inside the schematics of the Brayton cycle. We have that the diffuser, I'm going to take it as ideal. I have a compressor, which is not ideal. It has 0.8 in efficiency. The turbine has 0.85 of efficiency. And the nozzle, I'm going to take it as ideal, okay? I still have the combustion chamber, which is putting in heat that comes from a combustion, or a chemical reaction called combustion, and it will heat the air that is coming here. Remember, we can take that the Brayton cycle is using air. In this case, it's not completely accurate to take this as air all the time, because at 0 you have air, at 1 you have air, at 2 you have air, but then at 3 you have a mixture of fuel and air. There is so much more air than fuel, therefore we can still think that it's almost only air, but that's not completely true. Well, so that's one thing. Just for this example, we'll take as air as being just air, okay, without the fuel part at 3, 4, and 5. Well, now, if you remember, this thing is worked out with as an ideal gas, therefore we have the K and we have the CP. This CP, we also need to have into consideration that it's assumed to be constant all along all the states, 0, 1, 2, 3. Actually, the thermal capacity has some dependence on temperature. So if you are changing the temperatures, the value of this thermal capacity at constant pressure should be changing. But we can assume that this is not happening um, because it's a good approximation. Okay, I was going to say that there's not much temperature change. No, there's a huge temperature change, but nonetheless, CP doesn't change that much. If you want to have more accurate results, you need to use a function of the thermal capacity regarding the temperature. But this is for this type of problems. For the sake of this course, we can take it as non-changing. Okay, the CP is constant. Okay, more data. At the entrance, you are flying at a really high altitude. Therefore, the barometric pressure, the atmospheric pressure, should be lower than 101.325 kilopascals. Okay. Therefore, this has some meaning. Now, the temperature, if you are actually flying at really high temperatures, you will have a minus 32 degrees Celsius. That's kind of makes sense. You have a pressure ratio of 12. This happens between the compressor. So 1 and 2 will push you up the pressure 12 times from 1 to 2. You have the entrance velocity at, it's almost a typical commercial flying or cruising velocity. Okay, 320 meters per second. It's I was gonna say almost sonic. Okay, you almost got to that place, but no, still this is supersonic. But it actually depends on the temperature of the air. Okay, it doesn't really matter. You have the velocity at the entrance. You have the temperature, the highest temperature in the cycle, which is at 3. Okay, you come out of a combustion chamber, therefore you should have the highest temperature there. The mass flow of air at 0, 1, and 2, it's 60 kilograms per second. The heating value, okay, so this guy is maybe new for you. The heating value, it's a parameter, very important parameter for fuels. It will tell you how much energy the fuel will put out if it's burned. Okay, so it's an important parameter because you maybe want to know, okay, if I put wood into an oven, how much heat would I take from that? If I put coal, if I put diesel, if I put um, uh, you know other oils, other type of oils, what type of how much energy I'm going to take from those. In this case, we're going to use this value. Okay, so it's a typical natural gas value, I would say. You need to find, for this example, the velocity at 5, the power of propulsion. This is not the power at the compressor, not the power at the turbine. It's the power for the propulsion, because this is actually what this thing is intended for, to propel something, okay? And also, they want you to find about the mass flow of fuel that is happening here at the combustion chamber. So this QH comes from a combustion. That combustion means that some flow of fuel is being burned. They need you need to tell them how much that mass flow is for this example. Okay. Well, okay. I'm gonna jump right into the problem. So I'm gonna go with the diffuser. I'm gonna think that this thing is happening isentropically because the efficiency is 1 for the diffuser. Okay, so what I'm gonna write here is this: P0 1 minus K. This is an ideal gas, therefore I'm allowed to use this formula. So P1 1 minus K and T1K. Let's just see what do we have. Yeah, I have this one. I have this one. I have the K. Okay, I don't have pressure and I don't have temperature. Oh God. So this thing is a little bit tricky to start with. I don't know how much are things at 1. Oh, Jesus. So what should we do? You should use the first law for this diffuser. You can do it because you will have yourself that H0 plus V0 squared divided by 2 should be equal to H1 plus V1 squared divided by 2. And I'm going to use an assumption that maybe it seems a little bit brusque at first, but then hopefully it makes some sense because I don't have data for how much is the velocity at 1. It should be some value, right? It couldn't be 0. Nonetheless, I'm going to take this guy as approximately 0. It's not that it's 0, but compared with the 320 meters per second squared, maybe this V1 squared doesn't, it is not very relevant. Okay, that's why I'm doing this. 1, because I don't have data, and 2, because I'm thinking that the diffuser is actually what a diffuser is doing. It will use the kinetic energy in order to produce thermal energy. That's what the diffuser is actually doing. So it's not a really bad assumption to do this one, and I need to do it. Okay, so with this, I will get this. So maybe you will find V0 squared divided by 2 um, equals, let me just do it this way. So H minus 0. Okay, with this, I will get CP T1 minus T0. Now, hopefully you know that I have T0, I have the CP, I have the V squared, therefore I can get the T1. So T1 in this case, I have T1 actually equals to, you can put the name, the numbers there, and I have something around 292 Kelvin. I have rounded up a little bit. So T1 equals to 292 Kelvin, okay? Um, you come from 241 Kelvin. This minus 32 degrees Celsius is 241 Kelvin, if I'm not mistaken. Therefore, you have increased the temperature like 30 degrees Celsius or something. Okay, good. Remember that in order to do that, this is your unknown. So remember that you need to do this 2000, right? So remember this unit conversion, because otherwise you cannot compare meters per second squared with these fellas, which is kilojoules per kilogram. So remember this stuff and check that I have this number right. Okay, so I have that number there. And yeah, then what? Well, then I can skip to this part. Now I can go to that part and say, well, you know what? Now I can get myself the P1. So P1, I'm actually going to write it right away. So the P1 is actually, maybe I'm not mistaken, it's P0 and then T0 divided by T1. And this was K divided by 1 minus K. And I think I have everything because I have the entrance pressure, the temperature at the inlet of the diffuser, and I have this T1 that I just got from the first law. Therefore, by using this stuff, which is isentropically, I will have myself that P1 equals to 62.6 kilopascals. So if you notice, I have increased the pressure. That's basically the idea of getting yourself a diffuser, to increase the pressure by sucking up the kinetic energy. Okay, I didn't put any work inside this machine. I just used a conversion of energy. Okay, so with that, I have this one. The basic idea is to get everything from 0 till 5 in order to use this stuff, in order to calculate all these things that they are asking you. Okay, so that was from 0 to 1s. Now let's just go from 1 to 2s. Oh, what do you mean 2s? Isn't this compressor real? Yes, it is real, but nonetheless, you always need to use the isentropical case in order to compare. So I'm just going to write this 1 minus k T2s, k. I'm emphasizing that I'm going to get the temperature. Maybe I'm going to get the temperature. Hopefully, I'm going to get the temperature. So I know this fella. I just got it. I know this guy, T1. I know this P2. It's not that I know P2. Well, you want me, I can do it. So P2 equals to 12 times the P1. How do you know this? Well, this comes from the ratio from this fella there. Therefore, I'm going to put the number here, which is 751.2 kilopascals, according to me. Okay, so yeah, I have it. Now T2S is the one that I'm looking for. So T2S would be equal to, let me just see, pressure 1 divided by pressure 2, 1 minus K divided by K, and this one is T1. So you already know what to put. Remember, this guy should be in Kelvin, this guy should be in whatever, and this guy should be in the same whatever. We want to put kilopascals, put kilopascals. If you want to put megapascals, put down there megapascals too. Okay, so with this, you will have that the temperature at the outlet of the ideal compressor, which is not this case, it's this. So you already have the temperature at the outlet of an ideal compressor, but you don't have that, right? Well, okay, but you know that the compressor has an indicator of efficiency. So this is 0.8. Therefore, what you're looking for here is the T2R, the temperature, the real temperature at the outlet of the compressor. Okay, so remember your definition of efficiency for a compressor. It should be, I always need to do this. I always need to put more power into a real compressor than into an isentropic one. Okay, so this, I'm not going to explain you how I'm putting this, but hopefully you know it. This is just comes from the first law, okay? The first law for the isentropic case and first law for the real case. So T2R minus T1. So you know, you got it, you got it, you got it, you got it. No, you don't have it. Therefore, T2R, let me just see if I can do the algebra right. It's T1 plus T2S minus T1 and everything divided by the 0.8. Okay, so T2R, in this case, T2R is going to be equal to, yes, I have it here, 669.2 Kelvin. So you get the drill, right? You need to get from 0 till 5 all along doing all this stuff. Sometimes going to be easier and sometimes going to be a little bit harder, but you need to get to the fifth state. Otherwise, you will not be able to get what you're looking for. Okay, so you have T2R. Okay, we're good. We're good. So I think we have this guy. We have this guy, and we're there. Now let's just go to 3. Oh, what about 3? Yeah, you're right. You know what? Nothing about 3. I don't actually need 3. Oh, are you sure? Well, let's just do it. Let's see what do we have. Um, from 2 to 3. Let me just put 2 real, okay, to 3. Why not isentropic? Oh, well, because I know that the compressor is real. It's not isentropic. Then you can ask, then why did you do the isentropic case? Because I need it in order to get the real case. Okay, so if I know that this stuff is real, I will always try to use for the last calculations the real cases. So this one is real, yeah, and 3 is always real because it comes outside of a non-isentropic machine. Heat exchangers are just by nature almost non-isentropic. What do you mean by almost? Well, I mean, you can design some heat exchanger that may look as isentropic, but heat transfer is absolutely, even more combustion. So that's highly non-isentropic because it's non-reversible. Okay, well, okay. So you had that stuff, and let me just see if I can actually tell you this. But in the heat exchanger, you can say, well, you know what? What goes in is Q in, or what's the name that I put? QH. So let me just still use QH so nobody gets so much confused. So QH equals to the M, which M, well, M1 or M2 and M3. I'm going to think that M1, M2 equals to M3. Here is air, and here is air plus fuel. Okay. But I'm going to think, guys, I'm going to think that I can approximate this stuff as non-fuel whatsoever. So this is M2. I can actually do it in a more accurate way, but it's more detailed and it's a little harder problem or longer problem. So I don't want to deal with those details right now. I just want to show you this. Okay, so CP is T3 minus T2R. If you know, you have everything set so that you can get the QH. It's not the most accurate QH because this M2 applies for 2, but doesn't apply completely or exactly for T3. Nonetheless, it's a good approximation. I will try to show you that. So QH equals to, I think I have it here, it's around a 400, I'm sorry, 44,067 kilowatts. Okay, that's the amount of heat, the power, the heating power that comes from the combustion into the air. Remember, you have used here the air. Okay. Okay, so what? Oh, nothing. I'm just telling you something that happened from 2 to 3. Okay, let's just move on. Yeah, let's move on. Let's go from 3 to 4s. What are you doing the isentropic? I need it. Why didn't you put 3s? There is no 3s. There is no isentropic case that goes from 2 to 3. So there is no 3s. So 3 is just real. 3 is just real. It's just the real state. Oh, okay, so good. I'm going to put this P3, 1 minus K, T3K equals to P4, 1 minus K, and this is T4SK. Okay, let's see what do I have here. So P4, let me just go here. P4, no, I don't have P4. Nope. No, you don't have P4? Wasn't it just P0? Oh, no. This is something important. So P4 is not P at the entrance of the diffuser. It was like that in the typical Brayton cycle for production of electricity, okay, but not for this case. Yes, P5 equals to P0, but we are still not there, okay? So you can assume this safely. You cannot say this, okay? So let me just put a big freaking no, okay? So no for that part. Okay, that's one change. Not, not just these elements here, diffuser and nozzle, but that's another consideration that you need to do in this type of Brayton cycle for propulsion, okay? P4, it's not P0 or at the entrance of the diffuser. Okay. So what should we do? Oh, maybe you can say, well, then P4 equals to P1. Well, maybe you are right, but I wouldn't risk that. You can assume something, and this is new. Okay, this is new for this type of problem. Let me just go back here. So you don't have this P4 and you don't have this T4S. Okay, you don't have it. P3. Let me see if you have P3. Yes, you have P3 because you have P2. And if you remember your heat exchangers tend to be isobarical. They don't say they are not. So I'm going to take it as they are isobarical. This combustion chamber is isobarical. So yes, P3, you have it because you have here pressure 2. Okay. Now, T3, yes, you have T3. It comes from the data, from raw data. Okay, so, but you're stuck. I don't know if you see this, but you are kind of stuck. You don't have it. Okay, so you will see, okay, what should we do? This is one way. I'm sorry, I was going to say. So you need to learn this for this type of Brayton cycle for propulsion. You need to include this part of the consideration. Otherwise, you won't be able to solve it. It is like this. Whatever power is producing the turbine goes completely to the compressor. So it wasn't mentioned. Well, if you study your textbook, it should be said that. But this is for Brayton for propulsion. Let me just put propulsion. So whatever amount of power the turbine would be producing goes completely to the compressor. So do you remember your backwork ratio thing? So WC divided by T. I don't know if you remember this for the typical Brayton cycle or the electricity production Brayton cycle. So this one is 1. For this one, I'm going to put again Brayton for propulsion. Everything that the compressor needs comes from the turbine, and the turbine doesn't feed anything else, because it could be, I don't know, maybe it could be feeding an electrical generator. In reality, yes, it does. It actually feeds a part of the electrical components of the plane, but most of the whole amount, almost the whole amount of the power produced by the turbine goes to completely feed the compressor. Well, okay, this is so very much important for this type of problems. It won't appear in the tests. They won't tell you, okay, so remember that the power from the turbine goes completely to the compressor. They won't say that. So you need to remember this for this type of Brayton cycle. Okay, so with that, I can write this. So if the compressor, I'm going to put MCP for the compressor is T2R, because I already know the real case, minus 1. This is the work for the compressor, the real one, should be equals to the MCP T3 minus T4R of the turbine. Okay, so remember about the signs. This one is positive. I force this guy to be positive. I know that the turbine has a negative work. Okay, I know that it's going out, but I'm just going to put it as plus because I don't want to disrupt this equality. Okay, this equal sign here. So I just force it. So there's no crime there. I just need it. So CP equals the same thing. M dot equals the same thing barely. Okay, so remember that we have done an assumption and we are saying that the amount of fuel is irrelevant compared to the amount of air. Okay, so with that, I can say that, okay, if you want me to put an approximation, I can put an approximation. But remember, you have this, you have this, you have this, but you don't have this fella. Okay, so let me just get the T4R. So the T4R will be T3 minus T2R minus T1. Okay, so T4R equals to 1022.7 Kelvin. Okay, it's really, really hot out of the real turbine. Okay, this is T4R. And you will say, well, so we got it, right? Oh, there's a problem there. Which problem? You still need to use this one. Why? Well, because I want to get the pressure. Oh, but you can get the pressure from, nope, nope, it's not a really good idea. So you still need to use this one. Okay, so let's use it. Oh, you cannot. Oh my God. So what do you want to do? You cannot so far because you still don't know this fella. And so therefore you cannot have the P4. So how can I get this isentropic? Oh, good thing that you have an efficiency. So let me just put it here. So you have an efficiency for the turbine. The efficiency of the turbine equals 0.85, remember? Therefore, equals to the work of the turbine divided by the work of the turbine. And I always need to do this. So for a turbine, a real turbine will always give me less than the isentropic one will give me. Okay, so with this, I can write mCp T3 minus T4R. And this guy is going to be divided by mCp, this is first law, T3 minus T4S. So yeah, thank you, thank you, thank you. Your go. So T3 is data. This guy is data, 0.85, of course. You know this. Oh, I'm sorry, I was gonna put no an X, but no, you actually know this data, but you don't know this guy. Okay, so let's get that guy. So for this one, you will have yourself that T4S equals to. Let me see if I have it here. Yes, I have it here. Is T3 minus T3 minus T4R. And this guy is going to be divided by the efficiency of the turbine. So this is the algebra. You put the numbers in there and you will find yourself that T4S equals to 956.1 Kelvin. It's a good thing that the T4S, the temperature at the outlet of an ideal turbine, it's less than the temperature at the outlet of a real turbine. So that means that the turbine, the real one, hasn't used, um, the turbine couldn't possibly take all the thermal juice out of the incoming mixture of air and fuel at 3. Okay, but ideal turbine would. Okay, that's why it has efficiency of 1, the ideal one. Well, so that's why you have a colder. You actually have a colder temperature at the outlet of this turbine. Yeah. So all these things in order to use again this one. So P3 1 minus K, T3K equals to P4 P4 1 minus K, T4S. Yeah, this is with S. How do you know? Well, this is an equation for isentropic cases. So this is going to be for S. So therefore, this is K. So now you know everything but one, which is the pressure. Now you can get the pressure. And you can say, well, what do I need the pressure? You need the pressure. You will see that. So P4 equals to P3 T4S. No, sorry, backwards. I can do it with the, with the exponent, but nonetheless. So T3 divided by T4S. And this is, guys, going to be, let me just see, K, 1 minus K. So if you put the numbers there, you will have that P4 is actually 197.7 kilopascals. Okay, good. So you promised me that I was going to use this P4, right? Okay, so yeah, so hopefully you're going to use it. Now, look at this. We have come a long way. So yeah, 0, 1, 2, 3, then 4. I think we have everything at 4. So let's go at 5. Okay, so let's go at 5. The nozzle, right? Yeah, the nozzle. So for the nozzle, you will write this P4 1 minus K T4K. Oh, let me just do it kind of more correctly. So 4R, yeah. Why? Well, because you can have it. So if you know how much is the real one, because outside of the turbine, it's a real turbine, and you have just find out everything about it. Therefore, it's 4R, and you go to 5. And let me just emphasize that it's 5S because the efficiency of the nozzle is 1. So with this, you will write P4 1 minus K T4R, okay, K, equals to P5 1 minus K and T5S K. You don't need to put maybe this real one here or S here, but in this case, it's helpful because you will know which number to put into this equation. Let's just see if we can do it right away. So P4, you have it. It's just here. T4R, you have it, it's here. P5, you have it. How do you know that? Well, nobody has actually told you this, but P5 equals to P0, that I put it there because it delivers the air plus the fuel, it delivers it into the atmosphere. Therefore, it needs to have the pressure of the atmosphere. Okay, so yeah, you have it, but you don't have the isentropic temperature. Therefore, T5S equals to P4 divided by P5. You're going to have to say 1 minus K divided by K, and this is T4R. Okay, so with this, hopefully I'm right and I'm not messing up with so many 5 and S's and reals and blah, blah, blah. So with this, I will get that T5S is actually 607.8 Kelvin. So out at the outlet of this nozzle is still really hot, 300 degrees Celsius or kind of, okay? So this is really, really hot. The pressure is the atmospherical, but the temperature is 300 or something degrees above the atmospherical. Okay, good. So the nozzle is being used to take the thermal energy into kinetic energy. That's why that's how this thing it's doing that. So now guys, we can actually start solving the problem. Okay, so the first thing that they're asking us is the B5. So they're asking us about B5. Let's just see if we can actually do it. I'm gonna take, so H4 plus V4 squared divided by 2 equals to H5 plus V5 squared divided by 2. This is first law for the nozzle. Okay, so this is for the nozzle. And let's see, what do we have? Remember our B4? No, we don't have the B4. Well, okay, so remember B0. Okay, B0 was 320 meters per second. Hey, what about one? We assume that the diffuser has slowed it so much down that we can say that V1 was pretty close to zero. So B2, so B3, so B4. Why? How do you know that these guys are actually approximately zero? Well, because we didn't take into consideration kinetic changes for these machines. We just took Cp delta T, therefore none changes in velocity. So we can say now that we have been assuming this so far without saying anything. We have been actually doing that, but we cannot say this, please. We cannot say this at all. Otherwise, it wouldn't be for propulsion. Maybe it is for electricity production, but not for propulsion. Okay, so with this, I will say that this guy is approximately zero. Therefore, this B5 is going to be like this. So H4 minus H5 equals to V5 squared divided by 2. Okay, therefore, I'm going to put this. So 2000, 2000, 2000, yeah, 2000. Why? Well, again, this guy is kilojoules per kilogram. This guy is, let me just do this. I have time. This, these guys here are kilojoules per kilogram. This guy over here, it's meters squared divided by second square. Okay, this one is the unknown. Everything, so this guy should be gone into these units. If you remember, 1 kilojoule per kilogram equals to 1,000 meters per second squared. Okay, so therefore that's why I'm doing this conversion, because I want to pass these guys into meters per second squared. And how I do that? Well, multiplying everything from the left side times 1,000. Okay, and then this is because this 2 is going here, and I'm gonna put Cp, and then I'm gonna put T4 minus T5. I'm gonna be more emphasizing with this, so this is the real one, and this is the isentropic because the nozzle was ideal. Remember, if the nozzle is not ideal, then you need to get yourself a T5R. Okay, well, now B5, and let me just put here the square root. With this, you will get yourself that B5 equals to, how much do I have here? Yeah, 913.2 meters per second. Oh, a lot. Yeah, a lot. Oh, So we started with zero, and by using the thermal energy, we convert this thing into 913.2 meters per second. Yeah. Oh, so this is supersonic, right? Yeah, this is supersonic, like Mach equal to 3, maybe. Oh, but the plane is supersonic. No, the plane is not supersonic, but the air leaving the plane is supersonic. Why is that? Oh, because otherwise it won't produce thrust. So it needs to be a higher velocity at the outlet of the nozzle than as it went into the diffuser. Okay, so B5, let me just emphasize this, that this is the isentropic case. Yeah, I'm not dealing with a real nozzle. I'm dealing with a ideal nozzle. Okay, so I had this, and this is my first, the first problem that I have solved here, the first calculation. Now, let's just go to another one. They are asking me about the propulsive power. This propulsive power is not the compressor, it's not the turbine, it's this. Okay, so first of all, I'm not going to tell you how much is this, but I'm going to start with the thrust. So the force of the plane equals to the mass flow of air, okay, times a difference of velocity. This is B5S minus V plane. This difference in velocity times the mass flow of air will give me the thrust that this thing is experimenting. So M equals to 60 kilograms per second. And then, yeah, I'm going to put the numbers. So 913.2 minus 320, which was the velocity of the plane. Well, it is the velocity of the plane because that's how the air is coming into the diffuser, right? So the force or the thrust is equal to they put T as in thrust for in the language of propulsion. But okay, so I just stuck with high school physics. So the force F equals to 35 35.6 kilonewtons. So I have 35.6 kilonewtons. Okay, they are not asking me that. They're asking me about the propulsive power. Okay, so now the propulsive power equals to the force times the velocity of the plane. This is how I got the propulsive. Okay, so I always do this. I always get the thrust and then multiply it by the velocity of the plane. And that's how I got this thing. Okay, so long story short, WP equals to, all this stuff. And this guy should be 11,390 kilowatt. This is the propulsive power. So if you wanna go faster, okay, if you want the plane to go faster, you need to put more power into it so that it can propulse. You can propulse it a little bit more. Okay. Okay. So this is B. One more. They're asking you something about the fuel. Okay, so they're asking us about, hey, could you please tell me how much mass flow of fuel? Oh my God, I'm putting for Spanish combustion, for combustible. But in this case, let me just English again this stuff, which is fuel. Okay, so for fuel, um, well, it's a little bit simple. The QH equals to the Q taken by the air, but it's also the Q delivered by the fuel. Okay, so QH got to the air, but it's produced by the fuel, so it's the same thing. Okay, it is the same thing if the efficiency of the combustion chamber is 100%. If the efficiency of the combustion chamber has some it's less than 100%, it means that there has been some heat leak out of the combustion chamber. But not in this case. I'm not going to take that case, which could be a really more accurate analysis. But in this case, I'm going to say that I already had this one. Remember, it happened from 2 to 3. So from 2 to 3, I got this guy. So this is, you can say that this is the 400. Oh my God, the 44,067 kilowatt. You can say that. Okay, good. What do I do with this guy? Okay, now that you know that, the Q of the fuel equals to the mass flow of the fuel times the heating value. It's really simple. In that, like that. This is your known. This is data. This is data, or at least you already calculated. Therefore, the M of the fuel equals to, let me see, this is the 44,067 divided by the 42,700 kilojoules per kilogram. This is kilowatt, and if you know this, and you know this drill, you will get yourself with 1.03 kilograms per second of fuel. Remember how much was your flow rate of air? So I will remember that for you. It's 60 kilograms per second. So which one is higher? Oh, this guy is much, much higher. I would say it's so much than that. Therefore, remember what I did? So M3 is actually the air plus the fuel. So 60 plus 1.03. So that's why I said, well, you know what? Let's just do this guy zero. Whether you take 60 or 61, okay, so the calculations can be affected, but how much can they be affected? That's why for your analysis, for the overall analysis, it is not very relevant to take this. It's relevant for this stuff, okay? You cannot say, well, you know, the flow of fuel is zero. You cannot say that because you have tools in order to calculate it. But to do the other calculations, you don't need to actually take into account the fuel. It's so much higher. And I'm going to wrap this up with some indicator that is useful in this type of combustion or yeah, for propulsion or for car engines or for diesel engines or for engines. It's an indicator. It is not part of this problem. Okay, I'm just telling you about it. So there is a ratio. Okay, a ratio which is called a ratio. You know, ratios are this operation that if you put the mass flow of the air divided by the mass flow of the fuel, this is called air fuel ratio. Okay, air fuel ratio, and it's important for this type of combustion engines. In this case, if you do this, it's going to be 60 divided by 1.03. So this number is around 58.25. So for Brayton cycle for propulsion, your ratio air fuel, it's so high, 58.25. If you know something about car engines or diesel engines, this figure, ratio air to fuel, it's around 14, not 40, 14, 15 maybe, 16 or something. But for gas turbines or for propulsion gas turbines, they are so much higher. Well, okay. So, and if you go to further, I don't know, to other types of propulsion that, for example, you for hypersonics, for the ramjets or the scramjets or something like that, I mean, you go to much more than that, okay? And then you will go to rocket and you don't use actually air, okay? So it's not relevant for rockets, but it's relevant for vehicles that are flying in our atmosphere. Okay, guys, so that's that's actually enough for today. So take care, guys.